Hello, everybody, and welcome back. Root Beer here, and we're going to be looking at problem number 5 to finish off part 2 of the Alberta High School Math Contest we have been going through. So, what have we got? Determine the smallest positive integer n for which there are real numbers, x1 through xn, that all lie between 1 and 4 inclusive, and which satisfy the following inequalities simultaneously. So, the sum of the x's is greater than or equal to 7n over 3, so it sort of grows as n grows. And the sum of the reciprocals is greater than or equal to 2n over 3. Interesting. So one thing that sort of immediately comes to mind, just because we're adding up a bunch of things and we're adding a bunch of reciprocals, is arithmetic mean and harmonic mean inequalities. I don't know if this is where we're going, but one thing you could do is you can divide both sides of these inequalities by n. And you have here the arithmetic mean, this is the average of all the numbers, needs to be at least 7/3. Okay? And for the reciprocals, you do the same thing. And we can figure out what the average of the reciprocals of these numbers is. It needs to be at least 2 over 3. So what does this suggest to me? On average, the x's need to be at least 7/3. So that's what, just a little bit more than 2. And on average, the reciprocals need to be at least 2/3. So what would that be? On average, they have to be at most 3/2. Wait a minute. What? 7/3, 2/3, yeah. So on average, the xi's need to be no more than 3/2, but they have to be at least. So this would be less. This is less than 2, but this is greater than 2. Okay, now I'm a little confused here. Interesting. Well, what can we do about this? Well, first, I'm going to try and put this out of my head because I feel like I'm misunderstanding something there. So let's ignore that. Let's focus more on what we've got. Now, we got what? The sum of them here, and then the sum of the reciprocals. And they're both inequalities on the one side, so I suppose you could add them up. I mean, certainly that's something worth trying. Then the 9n over 3 turns into just a 3n. So this would suggest to me that on average, each of these things plus their reciprocal is at least 3. But I mean, that's the same sort of flawed reasoning that led me to this, and I don't think that is helpful. Additionally, we're focusing well, at least I'm currently focusing a fair bit on these x's. And what we really care about is the n's. Where do the n's come into it? So maybe we should be focusing more on this n over here. Is there a way to, I don't know, sort of neutralize the x's? Well, unfortunately, the x's can be sort of anything between 1 and 4. But is there sort of an expression involving the reciprocals? Because the reciprocal for each of these xi's has to be in this particular range. So is there an expression we can use? I mean, sort of, you could say at most it's got to be something like 5. is an interesting observation you can make. And so we might have sort of at most 5n if you add them all up. And so the 3n on one side, 5n on the other, that would be kind of interesting. Or, you know what? One thing we could try is to introduce a little bit of symmetry. Now, 4 happens to be 2 squared. So what would happen if we did something like this? Let y equal xi over 2. Then we know 1 over yi would have to be 2 over xi. And then what would we have? Well, the sum of the y's would have to be equal to half of the x's, half of the sum of the x's. But that's at most 7n over 3. And so we multiply that by a half, or sorry, at least 7n over 3. So that'd be 7n over 6. So the sum of the y's would be 7n over 6. But then the y's, the reciprocals of the y's, would have to be twice the reciprocals of the x's. That'd be twice 2n over 3, and so that'd be 4n over 3. But something like xi over 2 plus 2i over x1, xi over 2 plus 2 over xi. This is sort of a nicer, more symmetric expression here. So I don't know if that might be nicer to work with. Because, so here's what I'm thinking. If you take something like xi equals 1, you get a half plus 2 over 1, which is 2 halves. But if you take the biggest the xi's can be, which is 4, you get 4 over 2 plus 2 over 4, which is also 2 plus a half. 2 and 1 half. So you sort of get an interesting expression. So the biggest... So what this is sort of like a parabola almost, not quite, but the smallest this can be is 2 when xi is equal to 2, and the biggest it can be is 2 halves. So, we do have to write this up. It's the written contest. So, here's what I might say. Notice that the reason we go with sort of the symmetric expression, notice by the arithmetic geometric mean, that well, let's use our y's. So yi plus 1 over yi is greater than or equal to the square root of their product. Which is greater than or equal to the square root of 1, which is just 1. And then, no, I'm not quite sure what I'm trying to say here. Okay, but then, yeah, so here's what I say. And by harmonic mean, one over yi plus 1 over well, got to do the full harmonic mean. Okay, we get this sort of an expression. So, but this over here is really just 2 over yi plus 1 over yi. Oh, no, never mind. I thought I had something interesting, but it turns out both of these just give me sort of a bare minimum for my expression. Okay, nothing I can really do with that. But is there a way to talk about how big this can get? Yeah, so let's say something like since the yi is positive, because remember the xi's, and maybe we should just be doing with the this with the xi's. The xi's are between 1 and 4. The yi's have a much more pleasing sort of geometric mean because they have to divide by 2, so they're between a half and 2. But the yi's are always positive. So let's let zi be something so that zi squared is equal to yi. Then what can we say? Well, we can see that zi squared plus 1 over zi squared is greater than or equal to 2. But if I add 2 to both sides, the left-hand side here turns into a perfect square. And so does the right-hand side. So zi plus 1 over zi is at least 2. No, that still doesn't really help me. I'm not learning anything. And what I'd like is to get greater bounds on these xi's. The problem being, just to remind you, because I've been whittering on for a fair bit, is they're asking me about n's. So I want to take the focus on the n's and off of these xi's. And now I'm spending so much time. I've introduced yi's and xi's. I think perhaps I should just go back to the xi's. What I'd like is to be able to sort of limit what the xi's can be. Okay? Or sorry, what this sort of an expression can be. I'd like to get a handle on this. Okay, so I'd like to be able to say, so I know for a fact that this is going to be less than or equal to 2. You get that'll be at its smallest when xi is 1. But I did like the symmetry of this expression. Okay. I know that this is at least 2, but it's 2 only when xi is 2. But is there something where we can say that's as big as? Or it doesn't get any bigger than this? So if the sum of two numbers is no bigger than something, well, sorry, the product of these two numbers is fixed. Yeah, so there we go. So here's my argument, and this is a decent writing argument. Okay, so since the product is fixed, we get a bigger sum when the values are farthest apart. So this is actually something that gets used every once in a while in questions where, if you've got two numbers that multiply to something, so you got two factors, and you want to get the largest possible sum of those two numbers, or the smallest possible sum. The smallest sum is when the numbers are as close together as possible, the square root of 12 in this case. The sum is as big as possible, and the numbers are as far apart as possible. In this case, something like 1 and 12 gives you 13, whereas if you used 3 and 4, you'd just get a sum of 7. So it's a sound principle that gets used in a number of questions. Okay. But there's a limit to how far apart these can be. So we can see that, and I used to call this yi, but we don't need that anymore. We can see the smallest this thing can be is a half, and the biggest it can be is 2. Okay. So I might say something like, notice when xi over 2 is a half, or even 2, then its reciprocal is equal to 2 or 1/2. They sort of switch. So when xi is 4, when my x is 4, the other expression becomes as small as possible, as small as it can be. It'll go to 1/2. You'll get 2 and 1/2. Or if xi is 1, then this expression is 2 and the other one is 1/2. And this is as far apart as they possibly can get, because they're both sort of stuck in this range. You can't get numbers further apart. So we conclude that this sum here is at most 5 halves, or 2 halves, 2.5, or 2.5, whatever you want to say. Okay? So that sort of gives me a bit of a limit onto the sums. Okay? Now we can see, what did we see earlier with the when I called them y's? So 4n plus 3, 7n over 6. So we can see that 7n over 6 is the sum of halves of these. 4n over 3 is the minimum of their reciprocals. But suddenly when I add these up, I'll get we group these together, we know that each of these is at most a half. So this is 5 halves over n. And so this should give me a little bit of wiggle room. Now 7n over 6, let's change this to 8n over 6. And you'll get a total of 15n over 6, which, oh, that's kind of cool. You get exactly 5n over 2. So it turns out each of these must reach its maximum of 5 over 2. And so that only happens when each xi over 2 is 2 or 1/2. And so xi has to be 1 or 4, those exact endpoints. All right, now we're cooking. Okay? But we got here, just to reemphasize, because we're trying to learn techniques and things like that, we got this by saying, gee, I really wish there was some way to get a handle on this bit in here so we could focus on n's at the endpoints. I was expecting this to be something like, 4n over 2 or something, just to give me a bit more wiggle room to deal with more minimums. But no, okay. So we know the xi's have to be 1s and 4s. So let's let, not n, let's say k equal the number of x1s, or xi's equal to 1. So n minus k of them are equal to 4. Okay, I suppose we can go back to the original inequalities, but there's no harm in sticking with these ones if we wanted to. You just have k of these expressions equal to 1/2, and n minus k of them equal to 2, but maybe we don't want to deal with the fractions as much. Okay? Now we'll actually have to get equality here. Okay? So we must have equalities for all of them. Okay? Because of you're sort of limited here. Okay? So this would be k times 1 plus n minus k times 4. And what was the other one? 2n over 3 is k times 1 over 1 plus n minus k times 1 over 4. All right, multiply both equations by 3 at least. So 7n is 3k plus 12n minus 12k. And down here, multiply by 3 and 4, I guess. So 8n is 12k plus 3n minus 3k. So 7n is 12n minus 9k. Or I guess 9k is 5n. And what does this one turn out to be? We put 5 n's on that side, it is 9k. Okay, that's fine. N and k are integers. So we see 9 has to divide 5n. 5 has to divide 9k. So 9 has to divide n because the GCD of 9 and 5 is 1. And similarly, 5 has to divide k. If I were to do something like let n equal 9, and k equals 5, we could check 1 plus 1 plus 1 plus 1 plus 1. And then you'll have 4 4s is 16 plus this, that'll be 21. And then that's 7 times 9 over 3, because that's 63 over 3. And 1 plus 1 plus 1 plus 1 plus 1 plus a quarter. Oh, you'll have 4 quarters here, so that's nice. So that'll be 5 plus 1, that'll be 6, and that'll be 2 times 9 over 3. These all work out. We did check, and it's important to check to make sure that we didn't miss anything, that maybe for some reason n always has to be even. But we check, and having this many 4s and this many 1s will work. We can see that that's going to be the smallest. So n equals 4, or n equals 9 is the smallest. And there we go. So it was a bit of a detour. I was a little too hung up on trying to get some sort of symmetry with these yi's and zi's, and I noticed I was just sort of going around in circles with the same sort of expression. So we backed up and we said, all right, what do we really want? We'd like to get a handle on these. So it's not hard to get a lower bound, but an upper bound is a bit harder. And then we realized, it's nice and symmetric. Their product is 1. That's going to be nice and fixed. And then because of the symmetry of the expression we chose here, it was not too hard to see the max is going to be 5/2, only achievable when xi is at its lowest or largest amount. So more generally, if we had a similar sort of thing with a bunch of inequalities and the xi's were within a particular range, what I would want to do is set up a nice expression, something like this, that's nice and symmetric and achieves its highest values when you use b and when you use a. Is this exactly the expression I want? So when I use b, I'll get root b over root a, and then root a over root b. And when I use a, you'll get this one here. So yeah. And so then you'd have an upper bound achievable exactly when xi is a or b. and the lower bound would again be 2. And so then, well, you just slowly add things up, and I guess obviously they designed the question so that this would happen here. But it'd be interesting to see if we didn't quite get the same thing, how to handle that, and what sort of wiggle room you have there. But I think that's it. So we're done problem number 5. So that's it for our part 2 paper. So hopefully it's been a good Alberta contest for everyone, and maybe you learned a thing or two. Either way, thank you guys so much for watching, and I'll see you for more math, be it more Alberta contests or maybe a nice Euclid paper. Who knows? I'll see you for more math in the future.